Hey there guys, this is Mr. Herbst here, and today my focus is going to be on using and manipulating acceleration problems. In this video we're going to go ahead and use acceleration problems to solve for different variables, which ultimately is going to be a big part of your test. So strap on in and here we go. Alright here guys, just like I've done in the past, I'm going to go ahead and remove my face because I want you guys to pay close attention to what's going on the screen. Now I'm going to go ahead and assume that you have seen our acceleration equation in class. To review this, acceleration, which we abbreviate with the letter A, is equal to our final velocity, which we abbreviate VF, minus our initial velocity, which we abbreviate VI. And all of that is going to be over our time, and time is usually measured in seconds. Another way to look at this equation would be A is equal to a change in V, change in our velocity, all over time. Remember that this triangle right here in high-level math means a change in. So to review acceleration a little bit, acceleration is simply a change in our velocity over time. Alright, so moving on here guys, these are the four equations or problems that I'm going to go ahead and walk through in this video. If you need to, take a second to pause the video and write down these four problems that I'm going to go ahead and do in this video. Alrighty here guys, I'm going to go ahead and move on to our first problem right here. What is the acceleration rate of a car that increased its speed from 15 meters per second to 55 meters per second in 5 seconds? Now the first thing that we do in order to do this problem correctly is we make ourselves a list of the variables that we know. In our acceleration equation, there are four variables. We got A, we got VF, VI, and T. So we make a list of what we know. A is equal to, VF is equal to, VI is equal to, and T is equal to. The next thing we go ahead and do is plug in the things that we know. To do this, I first like to start at underlining the numbers that are given to us. In this equation, or this problem right here, they gave us three different numbers. The one that should be really screaming at you right off the bat is this one right here, 5 seconds. You should know that that right there is a measurement of time. So T is equal to 5 seconds. The next two numbers right here are both in meters per second. When you see meters per second, that should be screaming at you that that is a velocity. If we remember, our velocity equation is equal to a distance over a time. Distance is usually measured in meters and time is usually measured in seconds. So these two are velocities. So they're VF and VI. But the question is, which one is VI and which one is VF? Well, if we read carefully, if we're going from 15 meters per second all the way up to 55 meters per second, you might be able to see that 15 meters per second is our starting velocity, otherwise known as our initial velocity. So VI is equal to 55 meters per second, and VF is equal to 55 meters per second. So the thing that we do not know in our velocity problem right here is A. We do not know our rate of acceleration. So that's what we're going to be solving for. So I'm going to go ahead and plug everything into our velocity or acceleration problem right here. So we have simply A is equal to VF, which is 55 meters per second, minus VI, which is 15 meters per second, all over time, which is 5 seconds. Now the first thing that you guys are probably going to want to do is do this top part, 55 minus 15. That part is easy. So after we do that top part and we solve for 55 minus 15, we would be left with 40 meters per second on the top, all over 5 seconds. So here's what we have. We have 40 meters per second per 5 seconds. So let's go ahead and solve this out. 40 divided by 5 is 8. So 8, so I'm going to go ahead and finish it up right over here. So A is equal to 8 meters per second all over seconds. Another way to write this right here is A is equal to 8 meters per second squared. That is our ending acceleration. On to problem number 2. Problem number 2 is a little bit tougher. It says that if an airplane takes 10 seconds to take off from rest and accelerates at a rate of 9 meters per second squared, what is the velocity of the airplane just before takeoff? So once again, guys, we're going to make ourselves a list. A is equal to, VF is equal to, VI is equal to, and T is equal to. And once again, what I do like to do is underline all of the numbers that they gave us. In this case, we have 2 numbers in this problem. 10 seconds should be screaming at you that that's a time. So T is equal to 10s. The next number that they're giving us here is 9 meters per second squared. Whenever you see 9 meters per second squared, you should know that that's another way to say 9 meters per second. And that should be screaming at you that that right there is an example of an acceleration. 9 meters per second squared. The next thing that we do is we want to figure out what we know between VF and VI. Now here's the thing that makes this part kind of tough. You have to read the problem carefully. It says the airplane takes off from rest right here. The key word there is rest. If an airplane is starting off from rest, what would its initial velocity be? Well, hopefully you guys can see that if an airplane is starting from rest, its initial velocity would be 0 meters per second. So here's the thing that we do not know. We don't know the final velocity. So let's plug everything into our equation. We are given 9 meters per second, and I'm going to go ahead and write 9 meters per second, or 9 meters per second squared like this. You'll see why in a second, and then I'll show you how seconds will cancel. 9 meters per second is equal to our final velocity, which we do not know, minus our initial velocity, which is 0 meters per second, all over our time, which is 10 seconds. So ultimately here, guys, what we're solving for is VF. We want to know this right here. So here's what we do. In order to get VF by itself, or solve for VF, we got to get rid of this 10. In order to get rid of that 10, what we do is multiply by the reciprocal on both sides. So 10s over 1 will cancel out 10s on this side. And what do we do over here? What do we do to when we do to one side? We got to make sure we do to the other side as well. So 10s over 1, we multiply that on both sides. Now, if you guys remember if you remember back about the factored label method, remember when we have one thing on the top and then another thing on the bottom, and they're the same, would they go ahead and cancel? So what I'm saying here, guys, is seconds is going to cancel out. Now we go ahead and do our multiplication. 10 times 9 meters per second divided by 1. It sort of looks similar to our factor label method. 10 divided by 9 is 90. And our units here are meters per second, all over 1, which ultimately is the same thing as saying 90 meters per second. And all of that is equal to VF minus 0 meters per second. Now, a lot of you probably can guess that, hey, 0 meters per second just kind of goes away. But in order to do proper algebra and to get VF alone by itself, you have to add 0 meters per second to each side. So once you do that, you will be left with 90 meters per second is equal to our final velocity, which is what we need to solve for. So now we go ahead and we know VF. So moving on. This is a complicated problem. It says that Mr. Herbst accelerates his walking speed in the hallways in order to pass some slowpokes. He accelerates at a rate of 10 meters per second squared to a final velocity of 1.5 meters per second in 0.25 seconds. And it asks, what was Mr. Herbst's initial velocity when he was stuck behind the students? Once again, guys, we follow the rules. We make ourselves a list. A is equal to, VF is equal to, VI is equal to, and T is equal to. And then we go ahead and plug and chug what we know. Once again, I like to underline the numbers that we know in this problem. This one right here, 0.25 seconds, should be screaming at you that that is an example of a time. 0.25 seconds is an example of a time. Then we go ahead and look. Well, we are given another number here, 1.5 meters per second. And take a look. It even tells us that it is a final velocity. So we know that we are given VF, which is 1.5 meters per second. Then we're given this number right here. Once again, when we're given meters per second, or meters per second squared, that should be screaming at you that that is an example of an acceleration. So we're given A, which is 10 meters per second squared. So the thing that we do not know, the thing that we are solving for in this problem is VI. So once you know that, you can plug and chug everything into your acceleration equation. So 10 meters per second all over seconds, or 10 meters per second squared, is equal to our final velocity, which is 1.5 meters per second, minus our initial velocity, which we do not know, all over our, which is 0.25 seconds. Now, once again, we are solving for VI, so we need to get VI alone. In order to do that, we got to get this out of the bottom. So we multiply by the reciprocal, which is 0.25 seconds all over 1. Well, what you do to one side, you got to do to the other side, so 0.25 seconds all over 1. Now, if we're left with this, seconds will cancel, so we do 0.25 times 10 meters per second, and if you multiply that out, you'll be left with 2.5 meters per second is equal to 1.5 meters per second minus VI. Now you can do one of two things. I'm going to go ahead and do what I believe is easier to do. Once again, we need to get velocity, the initial velocity by itself. And we have a negative, which makes it a little bit of a problem. If we go ahead and add VI to each side, it will get rid of that negative right there. So we add VI to each side. So after we do that, we'll be left with VI plus 2.5 meters per second is equal to 1.5 meters per second. Then what we can do is subtract. Then what we can do is simply subtract 2.5 meters per second on each side. And if you go ahead and solve this out, VI is equal to negative 1.0 meters per second. And that's how we would show proper work for that. Okay, guys, moving on to our final and last problem. This one is probably going to be considered the toughest of them. It says we want to know how long does it take a car to reach a cruising speed of 30 meters per second from rest if the car is accelerating at a constant rate of 6 meters per second squared. Well, once again, so we follow our rules and make ourselves a list. A is equal to, VF is equal to, VI is equal to, and T is equal to. We need to know those four things right there in order to continue. Then what I like to do is underline the things that we know. We are given these numbers right here, 6 meters per second squared and 30 meters per second. Once again here, guys, anytime that you're given a distance divided by a time or time squared, you should be knowing, that should be screaming at you that that is an example of an acceleration. So A is equal to 6 meters per second squared. The next number that we have here is 30 meters per second. How do we know if 30 meters per second is VF or VI? Well, we go ahead and read what's around it. It says that the car starts from rest and it reaches a cruising speed. So what we need to know here is that the car is starting from rest. If a car is starting from rest, what does its velocity have to be? Well, it has to be 0 meters per second. And then it's reaching a cruising speed of 30 meters per second. So the thing that we do not know is time. Another way to look at it is how long does it take? Or how much time does it take a car to reach a cruising speed? That's what we want to know. We want to figure out time. So let's plug everything that we know into our equation. So we're given 6 meters per second squared, which is equal to our final velocity of 30 meters per second minus our initial velocity of 0 meters per second all over t. Now the first thing and the easiest thing to do is going to be to multiply this numerator right here. Or solve out this numerator right here. 30 meters per second minus 0 meters per second. That simply is 30 meters per second. Once again, we have that over t, and that's equal to 6 meters per second squared. The next thing that we need to do is multiply t out of the problem. So what do? We multiply t over 1. That'll get t to cancel. What we do to one side, we got to make sure we do to the other side. So we would be left with t times 6.6 meters per second squared is equal to 30 meters per second. Then we can go ahead and divide 6 meters per second squared by each side, 6 meters per second squared. Or another way to look at 6 meters per second squared is to look at it as 6 meters per second. Now, if we take a look at this problem right here, what do we have on the top? We got meters per second, and we got 6 meters per second along the bottom. So meters per second is actually going to cancel, leaving us with just seconds. 30 divided by 6, I'm going to go ahead and do that over here, is 5. And then what is our ending unit? Seconds. So our ending variable right here is 5 seconds. The thing that we wanted to solve for was time. If you want to check yourself, go back and look for the thing that we were solving out. What were we looking for again? Well, we were looking for time. If your ending variable is not in a unit of time, for example, this one is in seconds. If this is not written in a variable of time, you did not do this problem correctly.